Great, great. Thank you so much, Professor Ng. Let me try to share my screen. Can you see my screen now?
Yes, we can.
Fantastic, great. So it's a great pleasure to talk to all of you this morning. It's always challenging to talk after a professor's work, because he got such a breadth of interests, and of course he it's I cannot really cope with so many tasks, but one task he couldn't talk about is his research, which is extremely exciting. He shared it with us just recently, and what he does in AI is really exciting. So let me focus on mainly on research, and at the end of my talk I will talk a little bit about AI as well, but generally my talk about the future of material science. And material science is, of course, is extremely strong in NUS, and I should say that there are many different topics of material science which are covered in NUS. And probably one advice to the PhD students is, don't choose the subject of your research simply because you read somewhere in the newspaper that that's going to be the future most popular topic. It's just that's completely wrong. There are no interesting or non-interesting topics, because there are still lots of unknowns in pretty much any field of research. The way how you should choose the topic for your PhD is what you like the most, what you're most excited about. And then any topic will lead you to great discoveries. And if you're not excited about this, then even the most interesting topic would be boring for you. Okay, let's talk about materials for now. So why materials are important? Well, it's actually since early on, materials were crucial for the development of the humankind, and we even call the ages we live by the name of materials. You remember the Stone Age, the Bronze Age, the Iron Age, and it's a good question. How do we call our age? How do we call the time we live in now? And probably for the first time in history, we have a choice. And one thing we probably need to make a good choice. Do we call it the digital age, or the silicon age, or maybe the nuclear age? But if you think about this, maybe it's time not to make a choice at all. Maybe it's really we need to diversify a little bit. So why do we need to make a smart choice, and why is it dangerous really to bet on single material? Well, I'll give you a small example. So here is the silicon technology, and here is the periodic table with all the elements which were used in silicon technology prior to 1990. So you see there are only 6 of them: silicon, of course, then boron, phosphorus for doping, aluminium for interconnects, and oxygen, hydrogen for passivation, and so on. So very simple technology, probably even I could master it. Now, after 1990, the density of transistors started to increase quite rapidly. We needed different interconnects. We used copper for interconnects, but still the basic of the technology is the same: silicon, which you dope with boron, phosphorus, and so on. And these days, the technology became extremely complex. So we use half of the periodic table for our silicon technology. We basically keep changing the old technology which started to develop from 1950, and we adapted and adapted and adapted for our modern for our needs, and at the same time it becomes more and more complex. And the question is, do we really need to try to change the old technology, or maybe we need to start to create some revolutionary new ideas, new technologies? It's even more burning question if we compare the elements which we use in our silicon technology with the elements which are found in our body. Okay? And you would be surprised, but we use more different elements, different chemicals for our integrated circuits rather than we have in our body. And of course, you would agree with me that human beings, if you consider them as a machine or as a computer, are capable of many more things than even the most advanced silicon process. So it's really important to make a smart choice and not to be slaves of one particular material. And these days, that's exactly what is happening. There are only few materials which determine our world. Like all our electronics is silicon. Most of the construction which is around us based on steel, aerospace, it's mainly aluminum. So we really we're dependent on very few materials, and those materials, the properties of those materials, really determined a lot of things around us. It determines the type of the devices, electronic devices we have. It determines the shape of the buildings we create, because they all are determined by the strength of the steel structure, and so on and so on and so on. So really, it's those few materials, they provide a lot of limitations, because when a designer needs to develop a new device, he or she needs to think, okay, what silicon can do for me, and then work within those restrictions. Ideally, of course, you would like it to be completely the opposite. You would like to start with the idea of what do you want your device to do, and then choose the suitable material for it. And this technology does exist. We call it composite materials and heterostructures. They do exist in electronics, in construction. We started to use composite materials for aerospace engineering as well, but still it's not that widespread at the moment. Ideally, what you want is really to create materials from scratch, really design a material by atom, or at least layer by layer engineering, because then you can say, okay, I want this particular layer of atoms to do one function, this the other function, and so on, and then create functional material which has specific properties, specific application. I mean, it's similar to the custom manufacturing, which we have already now. With the advent of the 3D printing, we started to use a lot of custom design, custom manufacturing, and these days you can draw anything on your computer in the comfort of your office, send this blueprint away, and then a few days later you receive your piece printed, created for you from scratch or by custom manufacturing. We started to do it with chemicals as well. You can, for example, design your DNA sequence and then send it away, and then you can you receive your small part of a DNA in a vial within a few days. So the question is, can we do it with all the materials we use? Can we create materials on demand? And here, let me just make a small diversion to my old field of research. Since some time ago, we used to work with graphene. Graphene is the first two-dimensional material. It's the thinnest possible material. It's only 1 atom thick. It's very simple material as well, consists only of carbon atoms. And despite its simplicity and its being only two-dimensional, it has a number of unique properties, like being most conductive, thermally conductive, being most impermeable, stretchable, strong, and so on. And all those properties really led to, of course, a lot of research, because it's the first two-dimensional crystal. It has unique electronic properties, so we studied its electronic properties quite a lot, but also it led to a number of applications, and these days those applications are really quite widespread. And of course, for us, for people who worked with this material from very early on, it's a very special material. But then when you look at the applications, it's not that special. It follows exactly the footsteps of many other functional or advanced materials before it, like carbon fibers or carbon nanotubes. It first started to be used in composite materials, like in sport goods, where you can pay premium. We joined forces with Richard Miller and McLaren to create this world lightest, unfortunately world most expensive watch as well, 1 million Swiss franc for 32 grams, definitely by far most expensive if you recalculate per gram. And but it was quite an exciting research and quite an exciting project for us. We also worked together with some car manufacturers to produce one of the world's fastest cars. And these days, graphene is really everywhere. So more than half of the models of Ford use graphene under its bonnet in composite materials to improve noise cancelling. And if you actually, it also can produce noise. So this is one of the interesting, most exciting startups which uses graphene for the headphones, where you get the highest quality of sound, because graphene is extremely light but extremely stiff material as well. So it produces very clean sound, and the sound range, the frequency range is extremely high. And then of course we all know this that most of the Huawei phones these days rely on graphene for thermal dissipation and thermal distribution. So so that's but of course we're looking for more and more applications of this material, and those are coming from very unusual areas, and we try to work on we try to apply this material outside of composites, outside of electronic applications. And one of the most exciting area for graphene applications is the membrane, because graphene is, of course, the thinnest possible membrane, and it's completely impermeable for any atoms or molecules. At the same time, we can modify it in such a way that it would be permeable for certain species. So you can actually turn it into a molecular sieve, and that's what people started to use some time ago, for example, for water filtration, or to make proton membranes for batteries, and they use it for DNA sequencing by DNA translocation through tiny pores in graphene, for drug delivery, and for biosensors. So, but what I really wanted to talk to you today is the future of material design. And the story goes like this, that graphene was first obtained by exfoliating graphite from with the Scotch tape, and graphite is the material which you find in your lead pencils. So of course the next question would be, what happens if you exfoliate other pencils? So the answer is that we can produce two-dimensional materials, one atom thick materials out of many other lead crystals, and we can have a full library of those two-dimensional materials with the range of properties: insulating, semiconducting, superconducting, ferromagnetic, and so on and so on and so on. So these days we really have a huge catalog of those two-dimensional crystals, and many of them readily available in the lab, and it's really exciting to study their properties, and that's a huge direction of research in NUS. There is one of the world's first two-dimensional material center in NUS, and it's really one of the most successful centers producing both exciting scientific research, but also working on many applications as well, creating spin-off companies regularly. But it also, those 2D materials, they also provide us with a unique opportunity to create future materials with the predetermined properties. Because if you think about this, you have those 2D crystals like a planar sheets, and you can play with them, and it's like a piece of paper, and the properties of those materials is like the text written on those pieces of paper. But then what you can do, you can put those pieces of paper on top of each other together to form like a book, and of course you can write many more stories in a book than you can do on a piece of paper. And that's exactly what we do these days in the lab. We produce so-called heterostructures, van der Waals heterostructures, by placing those 2D crystals on top of each other, and we start producing materials, artificial crystals based on individual 2D materials. And it's really, it's a very exciting direction of research, because you can combine many different crystals, many different materials together in one stack, and you can encode the properties of those stack with atomic precision, and you can have a variety of different materials together, and you can actually you can encompass different, you can target different applications and different properties with those heterostructures. And we work on many different heterostructures. We produced completely new devices based on them, so like tunneling transistors or solar cells, so or light emitting devices. So there are many of them. Those heterostructures which you can create are really very complex, and they can really do very complex functions, like emit light, for example, or you can sense light as well. And they already start to find their application, because the range of those 2D materials is huge. So you can cover different properties in different heterostructures, or you actually can combine all those different properties in one large heterostructure. So the sort of applications we're talking about are in silicon photonics, for example, where modulators based on graphene are already being designed for future ultra-fast telecommunication, because you want to move your signal processing from electronic domain into optical domain, and 2D materials really offer a very unique opportunity of the fast signal processing and signal modulation when you combine, because of the optoelectronic properties, when you combine those materials with silicon photonics, and in particular, what is interesting that you can use them as light sources, so because that's one of the major problem which exists these days in optoelectronic applications. So so there are a lot of research on the future of materials, and NUS is really one of the world leader in this area. But I would really like to make the next step and think what would be used in the future, and how can we what kind of materials would be on demand for the future applications. And here I would like to distinguish between the material properties and the functionalities which we use in our devices. And there is a difference, because materials properties is something which is fixed and it's given for a given material, and the functionality is the time-dependent property, which it's something which we use, which we want from our devices. So like they need to memorize something, or they need to do certain actions. And we typically in our current technology, we separate those two things completely. So we have the material which has properties, and then we change it into make a device which has the functionality. It's not, it doesn't work this way, for example, in biology, in human body, because the functionality here is really distributed throughout all the different levels. So you start from the individual molecules, individual proteins, so they all have, and then go into cell membranes, cells, organs, the full body. They all have their own properties and functionalities as well. So the question really which we want to study, and I think we would be very important for the future material sciences, can we create materials with functionality? So materials which can think on themselves and make some decisions, have memory functions, for example, and then if we can have that, we can build really structures based on those materials rather than on devices. And here we really have to go even beyond different 2D materials. We really have to use the full arsenal of the materials which we have, but they need to interact strongly with each other to create those extra functionalities. So we really work with different materials like zero-dimensional quantum dots or cage molecules, and one-dimensional like carbon nanotubes or polymers, 2D materials, of course, 3D materials without bulk, even live materials like cellular membranes, for example, or even individual bacteria. And then we try to combine them in a similar way how I showed you. We combine 2D crystals, but now we combine all the other materials together in an intelligent way to create functional materials which can produce certain operations, certain functions, and if you do this, those materials would be reactive to an external stimuli, but they can probably learn something as well and produce response, but also produce feedback and change their own structure depending on the particular stimuli which we apply. And then we would have those we would have the new type of materials which are reactive, which change their properties depending on the external environment. So I probably won't go too much into technical details. How do we do it? So there is a very interesting physics behind this, and it's a lot of math involved as well, and it's the technologies and the methodologies to design those materials are not developed yet. So there is a huge range of research which is in front of us, and we are really excited to look into this. But I would say that the possible applications of those smart materials are huge. It's the new type of electronics, so-called beyond von Neumann electronics, in memory processing. For example, you use memristor for neuromorphic computers, smart membranes, or energy applications, bio applications, and so on. And we already have first examples of those smart materials where we combine, for example, 2D materials and 1D materials, polymers, and we use those materials to produce smart antiviral coatings. And we already have the first results which demonstrate that our smart antiviral coatings indeed work, and they can kill 90% of the viruses within a short period of time. And generally, so we try to target many different directions, as I said, from membranes to electronics to energy. But at the same time, we try to develop the general methodologies, how to work and how to predict the properties and the functionalities of those materials. And it's not that easy. It's really, it takes a lot of development on the theory part. And one of the directions which we're trying to develop how to produce those new materials and predict their properties is the applications of machine learning techniques and big data, because big data and AI are being used in material research quite a lot these days, mainly in the design of the new small molecules with the particular functions, for example, for the pharmaceutical application. So these days, a lot of work on in the pharmaceutical industry use artificial intelligence and machine learning. So we're trying to reformulate this for the material discovery work. So we really have to figure out how to describe the material itself, how to describe its structure, and how to describe its properties. It's reasonably easy, even though it's not completely solved yet, to do it for small molecules. So we're trying to transfer these technologies to our artificial materials, how to describe them and how to describe their properties and especially functionalities, which is even more challenging. But then, of course, we really hope that we will be able to produce new materials with the predetermined properties and predetermined functionalities. And one of those would be phase-changing materials, and we can try to create memristor networks, the neuromorphic computers based on our functional materials themselves. So we're not only trying to solve the problem of the designer materials with the AI, but we're also trying to create new neuromorphic computers based on those functional materials. And of course, the challenging part would be, can we use those materials to solve the material itself? So that's really coming to the very basics of the intelligence itself. So I will probably stop here, and I would like to say that we currently actively working on the materials with the predetermined properties, and there is it's a very exciting field of research. Still, lots of unknowns and lots of exciting fundamental results, as well as interesting applications. But I think the future will be when we start to move from predetermined properties to predetermined functionalities, to make those materials do some useful work and have some basic intelligence like memory functions, for example. And those intelligent materials would be the future for many different applications, from smart membranes to telecommunications to computing to healthcare. Thank you so much for your attention, and I'll be happy to answer any questions now.
Thank you, Kostya, for a very nice talk. Audience, time for you to ask questions. You can either type in the Q&A panel. Kostya, you can also open up the Q&A panel to see whether there are questions that the audience have typed in. Or if not, can you please virtually raise your hand, and then I'll name you, and then you can unmute yourself to ask question in a live manner. So please take your opportunity to ask. Well, while you are pondering, I think, Kostya, thanks for mentioning AI. As you know, I'm professor in computer science and research in AI. So one question I kind of, maybe it's a fun question, is not, since you mentioned that a lot of this experiment could be in silico, and discovery. And would you think that one day maybe an AI program can get a PhD in material science?
Well, I really hope not, because I really want to leave something for the human. Mm-hmm. And you see, I mean, PhD, of course, it has two functions. One is to teach our students the basics of the scientific method, because of course when we teach people when we teach people physics or computer science for their bachelor and master degree, we give them basic information so they can go and start doing some work in a company. For PhD, we want to teach them how to do science, is the methodology of science. So how to design the experiment right, and how to formulate the question in a scientific way, and how to answer this. And that's probably what computers can do. But we also want our students to really actively participate in scientific discoveries. And unfortunately, there are no recipes these days how to make a discovery. And nobody knows where the discovery is coming from, and that's still unknown to us. I doubt you can program it. Whether a computer can accidentally stumble on the discovery, maybe, I don't know. But I really, for me, it's a mystery, and I really like to keep it this way.
Thank you for your vote of confidence on humankind. There are some questions in the Q&A board. One from Tanzin about how you describe difference between graphite and graphene. What process is used to produce graphene? And perhaps you can answer that also, maybe alluding to how maybe a human being needs to discover this difference rather than a computer.
Right. So the difference between so graphene is, you can consider graphene as a monolayer, one layer of graphite. So graphite is a layered material, and the reason why you can draw with a pencil is because it's layered, and you can exfoliate it easily, and that's what you do when you rub your pencil against paper. But its properties radically change when you go into one single layer, and that's so that's what is graphene, and its electronic properties are completely different, and so you can use it, but so its mechanical properties, it's very flexible, and it's very stretchable as well. And for example, you can use it as a flexible membrane, because you can make it permeable for some ions or atoms or molecules, and not permeable for the others. Right.
Okay. Thanks. Another question is about toxicity of the carbon. What is it? Let me see.
Carbon
Yeah,
nanotubes.
yes,
Yeah,
because
so
you mentioned
yes,
that. Yep.
indeed, that's a big problem, and yes, some time ago there was it was shown that carbon nanotubes can be toxic and can be cancerogenic. Actually, probably not toxic, but more cancerogenic. And the reason for that is very interesting, because when the body is trying to decide what to do with the carbon nanotubes, is try to the cells, they try to swallow it, and they look at it from a side, and from a side the diameter of carbon nanotubes is really a few nanometers, and they just they see it as a small object. But when they try to treat it as a small object, because it's so long, it cannot do it, and then they get confused, and that's the reason for its to be cancerogenic. But I would say that it's something which we need to so we do a lot of study with the 2D materials as well, whether those are cancerogenic or not. We so far the answer is no, but it's the research which is still in progress. And I would say that that's a general direction which we need to look at, because the answer is that in the future we're going to use a lot of nanomaterials. This is unavoidable. We use quantum dots everywhere, so lots of your screens are based on quantum dots now. So we use nanofibers everywhere. It is happening, and it's going to happen. So nanomaterials are going to be with us, full stop. And we really need to learn how to work and live next to those materials. So that's why there is a lot of research on the toxicity and of those materials.
Yeah, thanks. There are some questions that is a little bit more general, some questions that are technical. So let us, I think we have some time, so let us address some of the technical questions first. So there's one question from Go Yin Min. Let me read out the question in case the audience don't have the access to this. So the question is, many of the VDW heterostructures have appealing theoretical values, but are hard to realize in reality. How is NUS 2D Material Center pioneering the device manufacturing process? Excited to see the many successful applications, but I wanted to hear about how such a large-scale design can be made.
Right. So it's indeed true, but this direction is so this problem is both ways. So some of the devices are hard to realize in experiment, but some of the experimental results are hard to model theoretically as well, because those heterostructures are so large. And the answer is that on the experimental side, there are several directions of research. Of course, we work with increasing number of materials. We have glove boxes, and we transfer. We produce those materials in controllable atmosphere to make them stable and so on. But also at the same time, there are efforts to grow those materials on the large scale as well. So that's this work is being done across many researchers in chemistry, in physics, in material science, everywhere. And so there are really, depending on the particular property and the particular heterostructure, you would use different methods, either direct growth or direct transfer, and that's all those techniques exist in the 2D center.
Great, thanks. I hope that answers the technical question. We have two more less technical question, but not less important. One from Vaishnavi Ratish about thanks for the insightful presentation. Can I understand how can a young aspiring researcher with a background, not in material science, but in medicine and dentistry, contribute towards material science research? Are there any potential avenues for us, not in material science, in this research area?
Well, funny enough, I would say probably the most promising applications of 2D materials are exactly in healthcare, in many different aspects, like it's antibacterial coatings for implants, or artificial organs, artificial tissues, artificial membranes. So that's all the directions actively pursued in the world, but also in NUS. Funny enough, you asking about dentistry. So there are people in dentistry who are actually actively working and collaborating with people in physics on many different applications of 2D material applications. So there are lots of joint work between material science and dentistry as well. Again, studying different aspects from stem cell differentiation on different 2D materials to antibacterial coatings. So there is a lot of prospects there as well. But of course, you need to realize that it will be hard work, because you would have to be excellent in both worlds, in biology and in material science. It's these days, it's not enough to be expert only in one field. It's strongly multidisciplinary field, and people in material science, I always encourage them to look around and to learn more from biologists as well. So same for you. You have to learn a lot from material science as well.
Yeah. And I must say, you must also learn computer science, because AI will be the tool. All right. But actually, our graduate school is also quite interdisciplinary. We encourage cross collaboration, as Professor Costa has mentioned. So we have a few more minutes. Maybe I pick one fun question that is kind of that I embedded in my introduction of Kostya. So Han Chen asked about how you combine art with scientific research, and how does art affect your scientific research? Oh, we can answer that in 3 minutes. Okay, we have another talk at 9:45.
Well, I'm not sure if they affect each other, but there are different levels where they interact. So first of all, the type of science we do in material science, in nanotechnology, is require a lot of attention, manual work as well. You have to so there are lots of specialized tools which you can use, and that's sometimes, so it's sometimes you can see it as craft. And for me, the Chinese art, for example, where you really have to master your brush very very delicately and very intricately. So you really so there are some connections on that level, but probably the most fundamental level is again the origin of scientific and artistic intuition, the origin of the inspiration. And I think it has the same origin for both science and art, though I have no idea where is this origin.
Okay, thanks, Kostya. I think regardless of whether it's art or science, I think the constant thing is about discipline. I think that is also something that's important to do research and to do PhD. And the other is also creativity. I think creativity is important in art, but it's also very important in science, because innovation is all about creativity. So thank you all for questions. Thank you, Kostya. I know there are some other questions